Hello everyone, how are you? How's everything? I hope everything is going well with you. And all of you are ready to start the new chapter, which is going to be about the Z transform. But what is Z transform? Look, in the past few weeks, we spent a lot of time explaining the Laplace transform for you, and you realized that how Laplace transform could make our lives easier, especially when we're dealing with some complicated matters like differential equations or convolution and this stuff. Z transform could be considered the discrete time counterpart for Laplace transform. So the good news is that this is much easier than the Laplace transform. Let me explain for you how can we find the Z transform of a function. Look, this is the formulation that we use to find the Z transform. X of Z, capital X of Z, this is in Z domain, equals the sigma from minus infinity to infinity of x of n. Look here, we don't have t, we have n, right? Because we are in discrete time. Z to the power of minus n. You see, if you think about it, you might remember, okay, when we were in the continuous time domain and we were doing Laplace, we had integral of something, right? Integral of f of t e to the power of minus st dt when we were doing the Laplace transform. Here, you have sigma instead of integral because we're in discrete time, and x of n, z to the power of minus n. When n is going from minus infinity to infinity. Z transform actually extends the discrete time Fourier transform to the values of z, which are not equal to the unity. And I have proved this for you. You can find it in the lecture note 19. It's a very simple thing, but you don't need it actually. I just added it there for your general information. But when you saw DTFT, you know what it is, discrete time Fourier transform, right? Because if you remember, for Fourier transform, we had both discrete time and continuous time. Laplace was only for continuous time. Z transform is only for discrete time. So just keep this in your mind. And I already told you what was the formula. When it comes to the Z transform, okay, there are a couple of things that we need to find. When they give us a function, f of n or x of n, and they want us to find the Z transform of that, we need to find two things. We need to find the f of z or x of z, which is the function in the z domain, and also we need to find something called ROC. What is ROC? ROC means the region of convergence. You might ask me why, but I just want to remind you of something that you learned in your calculus 2. You remember when you were learning about the series in calculus 2? Over there, I'm sure that you remember sometimes some series could converge, right? Be converging, some of them could be diverging. So in this case, actually, when you look at the definition, look at the definition here, is the sigma from minus infinity to infinity of x of nz to the power of minus n. So it's going to be a series of infinite number of numbers, right? If this does not want to converge, so the answer is always going to be infinity. So it's not going to help us. We want a transformation that can help us, that can simplify our calculations, right? So we need this series to be converging. So the thing is, these series are not going to be converging all the time. They converge for a certain values of z, not for any value. So that is why we have to, when we are finding the Z transform of a function, we also have to mention that this is the region of the convergence for Z. Look here, we have, so you remember in Laplace domain we had S. So we have a new parameter here that we're trying to express our function in terms of that. Here we're expressing in terms of Z, but here in Laplace domain, if you remember, everything should have worked for any value of S. And that was what we were using it sometimes for partial fractions and these things. When you're using, we're actually assuming that it must be working for any value of S. Here the transform is not gonna work for any value of Z. It's gonna work for some values of Z, those values which are lying in the region of convergence. So I'm gonna explain to you by a simple example. Imagine x of n is a to the power of n un. You know what is function of un, right? Function of un is going to be 1 for n is greater than 0. For any value of n greater than 0 is 1. For any value of n smaller than 0 is going to be 0, right? So the sigma, if you want to find the Z transform of that, you will say x of z will be the sigma of minus infinity to infinity of a to the power of n un z to the power of minus n, because of the definition. I show you the definition again. Look, x of z is x n to the power of n from minus infinity to infinity of x of n z to the power of minus n. So in this example, what is x of n? X of n is a to the power of n un. And here is x of n, here is z to the power of minus n. So we have to find this sigma. Right off the bat, you say, now that I have un, I know that un is 0 for the values between minus infinity to 0. So those things are all zeros. So all we need to find is the sigma from 0 to plus infinity of a z minus 1 to the power of n. Why? Because it was a to the power of n, z to the power of minus n. You got it like a common factor from a z to the power of minus 1, everything to the power of n. Correct? Now I want to remind you again, think about your calculus 2 information. When would this thing be converging? For what values this something to the power of n, when n is going from 0 to infinity, is going to be converging? Of course, if this total value here is greater than 1, for example, if it's 2, think what's going to be. It's 2 to the power of 0 is 1, plus 2 to the power of 1 is going to be 2, plus 4, plus 8, plus 16, plus 32, plus 64, plus 122. It's going to be infinity for sure. Only if this value inside bracket is under 1, is smaller than 1, then the higher the value of the power, the smaller the number, right? For example, half 0.5 to the power of infinity is going to be 0, correct? It's like going to be 1 over 2 to the power of infinity. It's going to be 1 over 2 to the power of infinity. So it's like 1 over infinity is going to be 0. So if this value is smaller than 1, this whole series is going to be converging. What is the convergence? If you remember, if you had the sigma from 0 to infinity of x to the power of n, if x was smaller, if x was smaller than 1, it would converge to 1 over 1 minus x. Absolutely. So in this case, this is going to converge to 1 over your x here is a is to the power of minus 1. So this series, if if az minus 1 is smaller than 1, is going to converge to 1 over 1 minus az minus 1. So you can simplify it to this z over z minus 1. I just multiplied the numerator and denominator by z. 1 times z will be z. 1 minus a z minus 1 times it's going to be z minus a. But only for the time that a z minus 1 is smaller than 1. It means a over z has to be smaller than 1. It means a has to be smaller than z. Since we have to consider all the possibilities that a is and z, each of them is negative or positive, we say the absolute value of a has to be smaller than the absolute value of z. Because if it's not met, if this condition is not met, this whole thing is going to be not converging. This series will go to the infinity. So the z transform of this function will be z over z minus a for z's which are greater than a. Otherwise, so this is the region of convergence. As simple as that. This is the region of convergence. Z greater than a. For example, if a was 1, this number would have been 1 over 1 z minus 1, right? For region of convergence would be z greater than 1. So the z transform of a to the power of n un will be z over z minus a, and the region of convergence would be absolute values of z greater than absolute values of a. I think here you can see if you are showing, if you have a circle with the radius of a, these for these values for z's which are greater than a, this is going to work. But for the values that z is smaller than a, this is not gonna converge. So here is another example. Now imagine your x of n is given to you as this: minus a to the power of n u of minus n minus 1. So the main thing that changed here is this u of minus n minus 1. Mainly this thing is going to be 1 in the negative side, right, not at the positive side. So if I want to write the x of z, it's going to be the sigma of minus infinity to infinity of a, like I take minus outside, a to the power of n u of minus n minus 1, z to the power of minus n, right? This is from the formula. So now I know that this u of minus n minus 1 z minus 1 will be minus n from minus infinity to minus 1 of a to the power of n z to the power of minus n. Why? Because the u of minus n minus 1 is going to be 1 when n is smaller than minus 1. And it's going to be 0 for any values in which n is greater than minus 1. So now, can I do something? Can I say this thing, if I just change the sign of the n's, instead of n I write minus n, then it will be from 1 to infinity, right? So I can say it's minus sigma of minus n n from 1 to infinity of a minus n zn. I just changed the sign. So this is what I'm going to calculate. This is very similar to what we just did, right? What I did, what we did in the previous example, we had from 0 to infinity, and for that one we knew the formula. But here we're starting from 1. We know that if n was 0, basically if we had added a 1 here, at n equals 0, this thing would have been 1, right? Anything to the power of 0 is going to be 1. So the answer of this one, I can add a 1, right? And then write it from 0 to infinity. You get it why, right? In this one, we are talking from 1 to infinity. In this one I just added 1 because I'm gonna start from 0 to infinity, and we're in the negative side, right? Because it will add a minus 1 for us. So I just added a plus 1 to cancel that one. So I can say it's 1 minus this sigma. Why did I do this? Because I know the answer of this one. I just did it right in the previous example, right here. Right? For this case, from 0 to infinity, I know the answer. So here, I just adjusted it the way that I get this piece. So my final answer will be 1 minus a minus 1z, which if we simplify it, it's going to be like z over z minus a, right? So as simple as that, I could find the Z transform of this like more complicated looking function, and we saw that it will be equal to z over z minus a when z has to be smaller than a. In the previous example, z had to be greater than a, right? Here, z had to be smaller than a. Why? Because in the previous example, our answer was 1 over 1 minus a z minus 1. Here, it was 1 over 1 minus a minus 1z, right? So in this case, this value a minus 1z has to be smaller than 1. When this one would mean z over a has to be smaller than 1. So that's why z has to be smaller than a. So this is the region of convergence. And the Z transform is this value. So as you see, the answer looks very similar to the previous example, just the region of convergence is different. You see here the region of convergence would be inside this circle with the radius of a. In the previous example, it was outside, right? For z greater than a here, this is inside. So you see these two together, the algebraic expression of the transform and the region of convergence, these two together define the Z transform of a function. There are a few more examples on lecture note 19 that I will invite you to go take a look at them. The solutions are all there, so check them out. And if there was something which was not 100% clear to you, please come and ask me the details so I can explain for you in the online session. But I wanted to go over something very quickly, which is the properties of the Z transform. Look, there's a few, to be honest, most of them are obvious, but I'm just gonna tell you to make sure that you know them. Look, property number 1 says the region of convergence for the Z transform consists of a ring in the Z plane centered about the origin. You see most of them, all of those things, they look like this. There is a ring which is centered about the origin. So this ring, sometimes it could look like this, it could look like this, or it could be actually a ring. The second property is that the region of convergence does not contain any poles. You know what is the pole, right? Poles are the roots of the denominator. We worked with the poles when we were doing the partial fraction in the Laplace transform, you remember? Because why? Because if there is a pole in the region of convergence, then we're going to have division by 0, so we're going to have infinity. So it means that we're not going to converge. So this is very important. The third property says that if the function x of n in discrete time is of finite duration, the region of convergence is the entire z plane except possibly z either 0 or z at the infinity. So because look, those functions that we're talking about, they were not finite, you know, for example a to the power of n un, so it's going to go all the way to the infinity. But if it was a finite function, Most of the time, the ROC could be the entire Z plane. Just maybe this because just the poles will be excluded. Now it's a good time that I show you a beautiful thing about the Z transform, that actually now you will see that why Z transform is actually so cool and so useful. Look, imagine you want to find the Z transform of delta n. What was delta n? Delta n was only 1 at point 0, everywhere else it was 0, right? So we're going to find the n from minus infinity to infinity of delta n z to the power of minus n. So this is only having a mini-NAD n equals 0. So it's going to be 1, and z to the power of 0 is going to be 1. So the answer is going to be 1. Everywhere else is going to be 0. So look, this should, I'm going to tell you this because soon you're going to see how useful is that. Remember, the Z transform of delta n was 1, so the Z inverse Z transform of 1 will be delta n. I think it's familiar for you in Laplace transform as well, right? The Laplace transform, right, of delta t, it was also a value, right? 1. So here for Z it's as well, it's the same thing. So the Z transform of delta n is going to be 1. But what is the Z transform of delta n minus 1? So according to the formula, it's n to the power n from minus infinity to infinity of delta n minus 1 z to the power of minus n, right? But this thing is only non-zero when n is 1. So it's going to be 1 z to the power of minus 1. So the answer is z to the power of minus 1. So it gives you a tip if you want to find the inverse Z transform later on. The inverse of Z minus 1 will be delta n minus 1. So now you can easily guess the Z transform of delta n plus 1 will be Z. What is the Z transform of delta n plus 2? Oh, correct. It's going to be Z square. So this was actually a very cool feature of the Z transform. As you see, you can find many functions that transforms just by looking at them without any calculation. And even it's the same thing even for the inverse transform that I'm going to show you quickly later on. So now the fourth property, it's again something pretty obvious. It says if x of n is a right-sided sequence, right side, look, for example, it has a to the power of n un. Un, it means it's only happening on the right side of the axis. On the left side, everything is 0. Okay? If it's right-sided, and if the circle z equal r0 is in the region of convergence, then all the finite values of z, for which, of course, z is greater than r0, will also be in the region of convergence. Okay? But this same thing applies the other way around. If x of n is left-hand sided and this circle is in the region of convergence, then all the values of z for z between 0 and r0 will be in the region of convergence. But if x of n was two-sided, then, listen, this is important. And if this circle z equals r0 is in the region of convergence, then region of convergence will consist of a ring in the z plane that includes the circle z equals r0. Okay, so this one, for example, was for the right-sided, this one for the left-sided, right? If it's both-sided, it's going to be the common area between these two, which is going to be a ring around them, as you can simply imagine. Now, I want to tell you quickly about the inverse Z transform. The inverse Z transform, as I said, is super easy. Although, if you look at the formulation, okay, you see, okay, now I do have the function in z domain, I want to take it back to the discrete time domain. Okay, basically this z domain thing that I have is the f of x of n or to the power of minus n or whatever. Then you can apply the inverse of the same formula that you used for the z transform. You will end up getting this. X of n will be 1 over 2 pi j, the integral of x of z, z to the power of n minus 1 dz. But to be honest, you never need to use this. Let me tell you a trick. Imagine we want to find the inverse z transform of this 4z squared plus 2 plus 3z to the power of minus 1. You remember I told you the z transform of delta t will be 1. So of course the z transform of 2 delta t will be 2, right? 2 delta n. 2 delta n will be 2. Now we have z squared. It has to be delta n plus 2. So 4z squared is going to be 4 delta n plus 2. We have 3z to the power of minus 1. It's going to be 3 delta n minus 1. So this transform pair actually helps us a lot here. If you had something like this one, if they give you x of z is 1 over a z minus 1, this one of course you know how to deal with it, right? Because in the example that we solved before, the shape of a function should be like a to the power of n un, using that formula for the converging series. Look, this z transform, honestly, it's really a very simple operation, and there are several examples solved on lecture note 19. Please, if you need, you might need to watch this video once again, because when you reach to the end of the video, you will see that actually seems to be simple. Now go back and try to check out all these examples once again yourself, and you'll see you can actually manage to take care of the whole thing, because there is not much into that. For any function, you just find the z transform using the formula and region of convergence. For the inverse z transform, you either use this pair or you use this method that we use in the example. Thank you very much. I know I talked a lot. I hope you are not so bored, and have fun. Take care and see you soon.